we see here? What do you notice in those two signals? Those ones. There's something new there. Bad news. What?
The caption are in Chinese.
Japanese or Chinese?
Oh, no, well, just give a look at the picture. No, it's Japanese. What about the picture? Let's forget the caption. Let's try to describe it with our own words. What do you see? Look at the time scale.
Okay, that's fine.
Okay. Let's start. Those are minutes.
Minutes.
10 minutes. There's something new there. P waves and some converted to S waves are there, and they are here. You see? They're tiny. That signal is coming from a pressure gauge on the sea bottom. Toku event as a point source is here. Salute. That's Italian. And these are the two receivers that are recording the signals. So they are pressure meters measuring the variation of pressure on the sea bottom. So you see that on the sea bottom you can measure. What can you measure? Maybe some sound in the water, so P waves. P waves from a solid part, converted S to P waves there. So there is some tremor, and there it is. That's the earthquake. You can call them sound waves, seismic waves, that's it. But what's next? Well, it's long. 10 minutes. And it's 5 meters. So something is giving a pressure signal on the sea bottom. That's the tsunami. It's coming later, it's large, it's long period, very long period. Look, those are 10 minutes. So it's something totally different than seismic waves. Okay, I like this picture because it's coupling the system. Let's imagine to deal with what we learned during the wave physics course, and we have water, and here we have a sea bottom. Which waves are we waiting for? Oh yeah, you're right. Let's steer. No, it's a recording. Thank you. Which waves do you wait for? If you have a source. Come on, guys. Okay? So the receiver is here. Good. My question is, how can we explain those waves? Which kind of equation? Elastic wave equation? Okay. Let's give a look to what we did. I think we can use this one. Let's go back. So at the early stage of the representation theorem, we've been dealing with this equation, right? What do we have here? Okay. That's the stress tensor, so it's related to elastic forces. Deformations, acceleration. What was that? What forces? But I'm lazy, so we neglected that. Who cares about gravity? Let's start from an equilibrium. Let's measure vibrations for the stable from the equilibrium under the gravity, self-balanced. Let's go. Later on, we have been using F as a representation of a source. Okay? Representation field. By the way, what about gravity? Today's Friday. It's for lazy people, but we have to remember that gravity can be very important for liquids. So when you throw a stone in a pond, you're going to get ripples. Why? Because water under gravity field is creating a free surface and it does want to go back to the equilibrium. So gravity force is the main restoring force for liquids. So that today, I'm going to skip many of the slides that you have in the PDF. So I will try to take a sort of a short path. But we have to remember that gravity is there. And that's very important for liquids. Let me break the sort of a logic that was in the lecture, and let's start from high school physics. Now let's imagine that we have a sudden deformation of the bottom, okay? What does it mean? Like a thrust event in front of Japan, okay? So you're going to give a sudden kick to water. You should say, is it sudden? It was taking 2 minutes of the rupture to start and be completed, but it's very fast for liquids. So, really with very high school physics, you can imagine that you're giving some potential energy to a mass of water. How much? Well, it depends on the dimension of a kick, so the length of the fault and how much was the slip on that fault. But you're giving energy, gravitational energy, that then can be converted to kinetic energy. So when this is falling, part of the energy is going to create gravity waves. So the simple message to take home today is that tsunami is a gravity wave. Like the waves that are created by wind, like yesterday for example, in Bora, on the surface of water. But you can use exactly the same equations. Navier-Stokes equation, you did study Navier-Stokes equations. Okay, that's the first approach, for example. This is very simple. And if you want to take a very back on the envelope maths, okay, we can use an expression that we found very quickly when we discussed about energy and magnitude a couple of lectures ago. You can estimate the energy of an earthquake associated to a magnitude, okay, that's it. You can estimate the tsunami energy just as the amount of energy that is given as gravitational potential energy. So you can measure the delta H there, how much is the displacement of the water, the length of the fault, the wavelength, but for a fault like that is large. Okay, so the displacement is large, but if you put these very simple quantities there, you will get immediately that if you compare the tsunami energy to the earthquake energy, it's just a tiny percentage. It's tiny, but it's there. Okay? So when you have an earthquake, like a thrust earthquake on a subduction zone, you're going to displace part of the water. So you're giving part of the energy of the earthquake energy to water. And that's gravity is giving some potential energy, but it's going to be converted to kinetic. That's it. And the message to take home for tsunamis, for lazy people, is that when you compare the wavelength of this perturbation that is due to this, if you want, this section here, if you want to use like 10 kilometers or more, think about a large fault, 100 kilometers. If you compare it with the thickness of a water layer, well, that's large. And I'm assuming that you spent some course on fluid dynamics, so you did it, okay? And in this case, you can speak about shallow water. What is shallow? I don't know. For me, 2 meters is not shallow, but everything depends on the wavelength. So if you take 4 kilometers and if you take 100 kilometers, that's shallow. What about the height? The typical height of a tsunami in open ocean? Well, it's a couple of meters in the case of a large earthquake. You can say it's nothing. It's nothing compared, for example, to the thickness of the water. So they are tiny amplitude compared to 4 kilometers, shallow water gravity waves. And that's the summary. But they are very long period, very long. Long period and large wavelength. So that the energy that they are carrying, it's huge. It's tiny compared to the total energy of an earthquake, but it's huge. And the problem with tsunami is that okay, and we're going just to that point, before the terrible expression that is going to appear there, if you want to be lazy, the typical velocity of a gravity wave in shallow water is like that. And for an average ocean thickness of 4 kilometers, that's the velocity. Is that a nice speed? Well, depends. It could be fast. Not that fast compared to the seismic waves, and not that fast compared to sound waves in water. I hope you do remember, because we did study it in the wave physics course. So it's slow compared to sound waves. That's the end for today's lecture. No, it's not. Because actually, and again, you will have more slides on your PDF. Today we're going to skip some of them. If you want to attack a gravity wave problem in liquid with the standard approach, you have to go to fluid dynamics book to look for Navier-Stokes equations. That's one version of Navier-Stokes, and you can deal with that. I just was putting this because in most of the approximation in fluid dynamics, you assume that the fluid is incompressible. Is it really incompressible?
No, just something.
No, but you assume that it is incompressible because you want to study something that is lower than sound, because compressibility is given sound waves, okay? Like whales, you know. But in most of the cases, you want to study something that is lower, like that one, like gravity wave. So you can assume that in the incompressible case, those terrible equations can be written in a very simple fashion. Okay. What about the Navier-Stokes equations? Do you recognize something in these equations here that we studied also during this course? Thank you. Well, this part, but not this one, is actually what we discussed when we had been mentioning Q, or viscosity. So you're right. This part here is related to viscosity. What else? Well, actually, in the Navier-Stokes equation, there is something simpler than elastodynamics equations. Because in the equations that we have been looking just a few minutes ago, let me open it again. I think I closed it. Yeah. We have something similar to the gradient of pressure, but it's more complicated for us. Because we have the gradient in all the dimensions of a stress tensor. But in a fluid, stress is a tensor, is becoming something simpler, it's just pressure. And it's isotropic. So the gradient of the pressure is this term here, but simpler. Oh, I'm not saying that Navier-Stokes are simpler than elastodynamics equation. No, because they have this nonlinear term, that's advection, it's transport. In a solid, you're not allowing, on average, for transport. Okay? If I break it, I can move it. But otherwise, you're going to knock, transient, and then going back to the equilibrium. So we don't have this transport factor here. That's the advective factor. But what about this? Well, there you assume that there is a potential that can give some forces, body forces. That's gravity. So our F in isodynamic equations is this one, and this is the gravity potential. So something is similar to what we have been speaking about elasticity of solids. This term here, that's acceleration, of course. This term here is the gradient of our stress tensor, and these are our body forces. But usually we neglect. We have been neglecting them. Today it's time to let them work on liquids. Okay, by the way, if you are going to solve this equation for looking for a dispersion equation, that's it. That's the typical solution of Navier-Stokes equation. Why I'm showing this to you? Because here, traditionally, we can look for two extreme cases. Because this argument here is k, that is the wave number, that is 2 pi over lambda, and this is the thickness of a liquid. Now, we have two extreme cases. H is very small compared to lambda. What does it mean? That the wavelength of the signal that you're looking for is very large compared to the thickness. So that's called shallow water. And when H is small compared to lambda, this is going to 0. And the tangent, the hyperbolic tangent, is becoming the argument. So you just are having kh out of that function. The other extreme case is when h is much larger than lambda. So your liquid has a thickness that is huge compared to what? To wavelength. And that is called deep water approximation. And in this case, this is going to infinite, and this is going to 1. These are the two extreme cases in fluid dynamics. And in one case, the deep water, this is going to infinite, and this is becoming this. Why it's called dispersion relation? Because omega and k are related by something that is not a line. You do remember, I hope, with physics, we've been dealing with this plane here, and omega over k is velocity.
Yes.
And if it is constant, it's a line. For example, sound waves. It's constant. Constant slope. Whenever we move out of the line, omega over k is different than, that is group velocity, phase velocity, and wave dispersion. So another way to define dispersion is, okay, traditionally is when velocity depends upon frequency, or omega k relation is not a line. And immediately when you have dispersion, you have the difference between phase velocity and group velocity. And we studied that in the wave physics course. Okay, what about the deep water case? Well, we have a dispersion because omega and k are not a line. The ratio is not a line. It's something that is dependent upon wavelength, but in a very simple fashion here. Because, for example, if you define the velocity, you got this expression here that is a function of wavelength, so we have dispersion. And if you're going to compute group velocity, so this derivative here, you're getting just 1/2 of phase velocity. So they're not the same. On the other side, here, the shallow water, this is going to 0, this is getting out. Now omega over k is a line. And that's given. Once you have a fixed h, and you're staying in a gravity field, that's given. Now, is the thickness of the fluid layer or the liquid layer constant? No. Because the tsunami can be excited in a thrust zone with 8 kilometers of liquid, then it's going to the shoreline. So it's getting thinner. So it's getting slower. So it's going to be, how to say, increased by amplitude because it's reaching slower velocities. And that's why tsunami is terrible when it's approaching the shoreline, because 2 meters in open ocean can become 10 meters in front of the shore. You could say 10 meters, is that large? You can get 10 meters also with wind. In open ocean, wind waves can be 10 meters. But they are very short in wavelength. Well, not that short, let's say 100 meters, but a tsunami has a wavelength of 100 kilometers. So you have something that is not that large as an amplitude, but with a very long wavelength. So energy is large for a tsunami excited by an earthquake. By the way, what I'm showing here to you is that just using fluid dynamics, Stokes Equation, and if you're looking for gravity waves, and you're looking for the dispersion relation, you have 2 regimes. That's classic fluid dynamics. Deep water, shallow water. And nothing is mentioned in tsunami here. Okay? That's for every gravity wave in a fluid. What do you think? Which kind of regime is following tsunami? Deep or shallow?
Shallow.
But why? Most of its tsunami life is like a shallow water wave. H could be large, 4 kilometers, as I told you. Okay? An average ocean is 4 kilometers. What about K? 2 pi over lambda.
Since lambda is very large. So
Why is large? Because if you have a large fault, like in the case of a mega earthquake, the wavelength there, that is the amount of water, not the length, that's 1,000 kilometers, but the width of a fault zone in that case can be 10 or 100 kilometers. That's giving the wavelength, and it's kicking from the bottom, not from the top, okay? That's why this is the most of everyday life for an earthquake induced tsunami, it's living like a shallow water wave. For higher frequencies or shorter wavelengths, part of the tsunami life is like that, but it's not the most important one. Now, let me show to you the most important picture from a theoretical point of view for today. These 2 pictures, well, this one is coming from a PDF that you can find on the website, on the Moodle website. It's a very nice paper that is contained in an encyclopedia written by Stephen Ward, that is one of the most famous researchers dealing with tsunamis. So if you want the full story, is there. But the message for me to take home with you today is this. That's containing most of the thing. Now let's give a look. What do we have here? Well, we have 2 physical quantities, wavelength and wave velocity. And here we have period. Okay? Let's give a look. Seconds. From 1 to very long periods. 1,000 seconds, minutes, hours. And if you give a look to these lines here, these are nothing else than the dispersion relation that we have been looking at in the previous slide. And what do we notice here is that this line, that is velocity, is flat until a given period. Well, and it depends on the thickness of a liquid layer. 1 kilometer, 2 kilometers, 4 kilometers, okay, let's take 4 for example. You see that this line is flat, let's say until here. Why it's flat? Because actually we have no dispersion there. it's the square root of GH. So it's a number. And if you see here, it's about 200 meters per second. Now, at shorter periods, wavelength is decreasing. And actually here, as you can see, it's getting shorter periods, shorter wavelength, and now that's deep water regime. And if you give a look to the solid line and the dashed one, you see that they are different. Those are the phase and group velocity, and you see the group velocity here is half of the phase velocity. So shallow water is here, deep water is here. Now, what is deciding which part of these curves the gravity wave is following? The period. So if you're looking for standard beach waves, let's call them with that nickname here, they are about, let's say, 10 seconds. And if you give a look here, look at the wavelength, it's about 100 meters. That's large. So they can be very large. But actually, they're living in this window here, and you see that's the deep water. So they are large, but not that large if you compare them to 4 kilometers. So in open ocean, a wind-driven gravity wave, okay, can be 10 meters, can be 100 meters, but it's tiny compared to 4. Okay, 0.1 compared to 4. Wavelength is 100 meters. So what we have to compare is the wavelength here compared to h. If this is 100 meters, it's 0.1 kilometers compared to 4. This is tiny, so it's nothing. Deep water. If this is 100 kilometers, oh, wait a second, deep water, shallow water. That's why in this picture here, this gray band is called tsunami window. Look at the periods, 1000 wavelength, 100 kilometers, shallow water. So it depends. Now, what is deciding if gravity wave will be here or here? Period and wavelength, the source. So when you perturb the liquid from the top, for example, a meteorological perturbation, okay, you're kicking like wind, you're throwing stones like a landslide. They could be large, but not that large as a kick from the bottom of a giant earthquake. Long periods, very large wavelengths. So earthquake-induced gravity waves, you can call them tsunami, they are here. Let's give a look to what we can call eigenfunctions. If you do remember, I hope so, when we discussed dispersion relations in the wave physics course, we also called the problem eigenvalues and eigenvectors, like in the string case. Frequencies can be the eigenvalues, wavelengths are the eigenvectors. Okay, let's give a look to the eigenfunction. Let's give a look to very short periods. Well, not very short, but short compared to these ones. For example, 50 seconds, now we are here. Look at the trajectory that the gravity wave is doing, is letting the molecules of the liquid doing. It's round, it's a circle, and the ray is decaying with depth. So what you can say here is that this mode of a string is very large on the top and zero here. So if you want to play this mode, you have to plug the string upstairs, wind. If you go to very long periods, that's the eigenfunction. Now look, you have a very large x component of the motion, large but not the large vertical component of the motion, and yes, one component is going to zero, but this one is not zero here. So that string can be played efficiently here. So perturbation from the bottom is effective here, while perturbation from the top is more effective here. Wind-driven, earthquake-driven. But still they are gravity waves. But long period, large wave. So that's the summary of a tsunami. It's a gravity wave. Okay, I was skipping one of the slides there. And if you want to follow some nice animations that you can easily find on the web, what you see here is that most of the life of a gravity wave, long wavelength, shallow water, okay, or part of the deep water, what you're going to get is this dispersion, but it's tiny. Now, what you notice in this animation here is that long periods, these ones, are faster. We call that normal dispersion. If you want to understand why, they are here. These are faster than these ones, okay? So the long period and large amplitude, because the tsunami is traveling faster with this velocity here. Shorter periods, higher frequencies are here and slower. So that's why in this animation, you have this arriving faster than this. Easy. This signal is very easy compared to the seismic signal. Okay, what's next? Amplification, that's the other effect. With a sort of a technical terminology, you have to call that shoaling. And if you want to be more technical, it's called the Green's law of fluid dynamics. It's the same Green, but not for the Green's function, but for the Green's law in fluid dynamics. Let's take it simple. What do you have here? We have a fluid whose thickness is getting smaller. And if you take the square root of GH, that means slower. So this wave train is arriving here as getting slower. So the waves in the back want to push. And so you're getting larger. It's a conservation of energy. The energy flux is conserved. You have less surface, so amplitude is increasing. You can demonstrate that the amplification is going as the square root of a thickness, actually of the thickness ratio. So if H is getting thinner, the amplification is going with the 1 over, if you want. Okay? That's the Green's law. So it's a tiny amplification, but it's there. What does it mean? That if you have, let's say, okay, I was taking it. Okay? Let's imagine that you're getting a ratio between H2 over H1. Okay? You take this ratio, if it is 1, it's nothing, so it's constant. Let's imagine this is getting shorter, or if you want, take it up, and let's compute the 4th root of this. Okay? That's the amplification. It's called Green's law. By the way, a couple of meters can become easily, when you approach the shoreline, it depends on the steepness, of course, of the shoreline, but you can get easily meters and tens of meters, and this is what occurring in Tohoku. Okay, then there is the last part of the life of a tsunami, where you're getting to such a thin water layer, could be, let's say, 100 meters, 10 meters, and now the amplitude is comparable with the thickness. So you're going to break linearity. And you have to deal with amplitudes that are so large that the wave is breaking. You can surf. I wouldn't do that, but you can surf these ones, and they are entering inside the land. And that's the problem, because the bore formation will make the wave to penetrate, and you have a very long wavelength in the back. So penetration depth can be very large. And let me use this animation here also to define something that is very important, that is called tsunami run up. It should be here. I was putting that here. Because now we can go to this terrible slide here. That's the definition of a tsunami run-up. So you have to imagine something like that. So the steepness of this thinning of the fluid layer can be very gentle here, but sooner or later the amplitude will be comparable to the thickness, breaking of the wave and penetration. Okay, in terminology, we have to use a sort of the average water level. You can remove tides, that's it, so you have an average. You can measure the tsunami here, and usually this is called tsunami height, or maximum amplitude, or twice, okay? Peak to trough. That is called tsunami height. Still, it's in the linear domain. But when it's entering and approaching the land, if you have something like that, this height compared to this one is called tsunami run-up. Of course, run-up is dependent upon the morphology of the solid liquid boundary. So if you have walls, if you have a gentle beach, if you have a cliff, run-up will be different. So it's due to the interaction between the inundating liquid part and the solid part. But this is called run-up height, respect to an average water level. I know we can't read Japanese, but this picture had been released just a couple of days after the Toku-Oki event. And I was leaving this because this was impressive. Because if you look here, some heights are terrible. This is Tsunami Height. And I was keeping that slide, but maybe it's the case. No, okay, I left it here. Actually, most of these are tsunami run-ups. And this is this dot. Every dot is representing a measured run-up or height in the Japanese coast after the Tohoku event. And what is impressive is this. Because in some points, you can have a sort of a side effects due to the bathymetry, actually, the local bathymetry. So you can have also lateral variations of the amplitude due to resonances in bays, for example, okay? So you can have these very large points, it's much more than 30, but on average here it was, the red dots are 20. That's impressive. And so today I want to spend, and this is for the southern part, and these are the numbers. And in the remaining 45 minutes, I want to discuss with you, okay, we have been dealing with part of the physics of the tsunami, but it's relatively simple, okay, compared to the seismic part. And to think also about this physical phenomenon that is a gravity wave, long period, large wavelength, shallow water gravity wave, also in terms of hazard. Okay, you could say, wow, that's huge. Can we predict that? And this was the question, well, the answer was no. But unfortunately, maybe we could have been saying yes, because in the past, in Japan, as you can see here, in the Showa and the Meiji period, two events that, of course, as you know now, this is not an instrumental event, no recordings at the time. Also, if we are in Japan, that is the country that is, how to say, the more advanced in the study of earthquakes and tsunamis, at that time, for sure, there were no seismometers there. But evidences of run-up can be found on the coastline. And people who studied this, in some places you see, we have red dots that are as large as the 2011, as you can see here. So, what caused these heights and run-ups? And now, let me go back to, okay, let's also give a look to this slide that was supposed to come before. A modern, let's see, well, a standard modern measurement unit for tsunami is made, it's called dart buoy, and it's essentially this one. So it's a GPS that is floating, it's communicating with a satellite, so it's giving to you with very accurate precision your height. So you can measure tides, you can measure streams, you can measure a tsunami. What is important is that a complete dart buoy system is also coupled with a seismometer or a pressure gauge at the sea bottom, as you can see here. So you have a measure like the one that I've been showing to you at the beginning of this lecture, and okay, you can have the seismic part, tiny, fast, and then the perturbation related to gravity that can be measured here. And so the slide with which we started, this one, this is the signal associated to the change in pressure due to the fact that the liquid height was changing, so giving more pressure. It's lower, now we know, square root of GH. So it's coming much later than these perturbations here. Long period, look, these are 10 minutes, these are 20 minutes, thousands of seconds. And large wavelengths. Not because the velocity is large, but because the period is very large. So if you take 0.2 kilometers per second, but if you multiply them for 1,000 seconds, you get a wavelength that is very long. Okay? So now we can understand physically this. We can physically measure them with dart buoys. And Japan was severely struck by this tsunami, but they had, and they have, the most advanced tsunami warning system. But the point is this, that actually, after the earthquake, on the Japanese coast that you see here, you have, let's say, 15, 20 minutes to act. And really, the tsunami warning system that we have is very efficient. So in some minutes, with this piece of information, using P waves and S waves, so just after a few seconds the earthquake, they can stop Shinkansen, the high-speed trains, they can stop the elevators in the skyscrapers, they can do a lot of things, and if the magnitude is large enough, they issue a warning system for tsunami. And they are very well prepared in the sense of the education, because they learn how to react to this natural phenomena since kids. But they have just 20 minutes. Now, I cannot imagine any Mediterranean person able to act in 20 minutes, but they are very well trained to run to heights, to do whatever things, but still you have 20 minutes. And we are very well prepared to this event. Let me show it to you. So I'm jumping back and forth in this.
Just a question, like, it's not like every earthquake produces a tsunami.
No, that's the point. Oh, well,
Or
you can create a baby tsunami. If you get also in the Adriatic Sea, you can have in front of the Croatian coastlines, there are some faults that can give, let's say, magnitude 6. In principle, you're exciting a tsunami. It's a baby one. It's 10 centimeters. But pay attention, because you can say, who cares about 10 centimeters? Remember that the wavelength is not that short, and everything depends on the vulnerability of the coast. So if you think about some coasts, like in the central Italy coast, you have no defense, it's very flat. So penetration depth can be very long, also with 10 centimeters. Think about Venice. Acqua alta, I don't know how to translate it properly in English, can cause a lot of damage in Venice just with tides and some wind. So half a meter can be a large tsunami also if it is nothing for Japanese. But in principle, every perturbation of a gravity potential in a fluid is giving a tsunami. Could be a baby one, could be something that the Japanese were waiting for. They were waiting for tsunami. Do you know why? Because they built a lot of things like that. They have sea gates. They have tsunami walls.
So how does this one?
It's 9.3. Can you imagine? 9.3 meters.
Also, it's like crushing the wave.
Yes, you have other pictures. Tsunami walls. They had this. Sea barriers, like this one, they are huge. Now, is 9.3 meters enough? Can you imagine that? I can't. Well, I've seen that, but it's huge. Is that enough? It depends. Because actually that's the sad part of the story. As I told you, Japan is is and will be the most prepared country in the world for education, for technology, for whatever. They have been building these defenses since the 70s, after the 1960 Valdivia earthquake that was in Chile, that was hitting the Japanese coast the day after. They had been prepared. Prepared for what? For a 10 meters tsunami. I'm jumping back and forth in this lecture. Okay. Well, you know, it was not enough. In most of the cases, this huge 6 meters, 2 kilometers long, it was overcome by what occurred on March 11. What was wrong there?
Oh, so it's destroyed the wall.
Yes, this is in Miyako, but if you want to have some good news, this is another town, and this is Pudai, and this is a famous wall because it was defending the people in Pudai because it had been built taller than the courts. Because the mayor at that time decided to build according to the past earthquakes. And around Pudai there were these stones here. These are called Tsunami Sekior. These are the stone, you see this one? Because after the tsunami events that occurred in the Showa and the Meiji period, the elders were putting these stones saying, okay, look, please don't build after this stone. Okay, so it was a sort of a warning. It was one of the first examples of a seismic code, of a tsunami code. So the mayor in Pudai was remembering these ones, and so he said, no, okay, if in the past 10 meters occurred or more, let's build a taller. It was a huge debate about that one, because people were saying, come on, you're spending a lot of money for this. Do we need it? Well, they did. So that's the difference. Okay. But the point is again, you had been attending the seminar yesterday, and Tom Pratt was ending the talk. What to do next? What about Missouri and California? It's the same question that we had been asking together. Well, yes, the day before. So on wet. Who knows? Who knows? But in terms of hazard, definitely everything here depends on the maximum magnitude that you're waiting for. So, tsunami defense and tsunami risk reduction can be performed with tsunami barriers, right? You're not, and how to say, you're not eliminating the hazard. Your hope is to send to zero vulnerability. But you see, there are pros and cons here, because if your wall is not tall enough, vulnerability is extreme, because once the tsunami is overcoming the wall, it's staying there, or it's going to be broken. So, and it's giving to you maybe a sense of invulnerability. Because most of the Japanese, when the tsunami warning was issued, they were saying, okay, we are used to this, come on. Because the warning was given after a couple of minutes for a magnitude 8 earthquake. Okay, everyone in the world is scared by magnitude 8, but Japanese are not for magnitude 8, because they were not waiting for magnitude 9. That's the issue. So one part, a simple part of the story is this. I'm really jumping back and forth in my slides. Because now we know what is a difference of unit 1 in magnitude. Because magnitude is related to moment, and moment is related to the area and to the slip. So let's say that you are waiting, you are ready for magnitude 8. No country in the world is ready except Japan, maybe California, but okay? And they were ready for that. Now, as a very simple rule of thumb, as Stein and local, you received the homework.
Yes.
I hope, because I will ask you at the exam, okay? Some lectures ago, I was asking you to read the nice tiny paper by Emmy Local and Seth Stein about the Sumatra event. Now they published also this one. It's again a couple of pages. You have it there. I think I put it on the website. And a very simple rule of thumb for tsunami run-up is, okay, it's double the slip on the fault. Magnitude 8, on average, if you remember the Wells and Coppersmith plots that we have been looking together, a magnitude 8 usually has a 5-meter slip. So run-up will be 10 meters maximum. And Japanese were ready for 10 meters. But if you have a magnitude 9, on average, the slip is 10 meters, and the run-up will be 20, and they were not ready for 20. So, well, let me end this lecture with these final slides that are about hazard. But first, let me show to you a couple of other animations that are important. For example, this is the animation of what occurred on March 11 from the point of view of fluid dynamics. So no more strong ground motion that we have seen. If you remember, in the introductory lecture, I've been showing to you the ground motion. 6 minutes in Japan, do you remember? Okay. Now this is ground wave. This has been done by Kenji Satake and Bashir Fuji. Just a few days, let me show it to you again. You see that the wave field is relatively simple. Here you have the propagation, you're getting slower, increase of amplitude, and here you have some local resonances due to bathymetry, okay? And refractions, and stuff like that. How much time do you have to react? Okay, let's say 15 minutes, 30 minutes. It's nothing for most of the countries in the world, it's a long time for Japanese. They can do something. And they could do something, but they were waiting for 10 meters. And most of the people were saying, okay, we're ready for that. We have the walls. Let's drive a car just in front of the sea, as we have seen in there. They were quite relaxed. But in minutes, they realized that the height was not 10 in most of the places, and it was 20. So the defenses had been overcome. Let's take the good message home. Kenji Satake, just a few days after the event, started with modeling, and he also started the comparison with the available measurements. So in blue, well, most of the measurements were not available because the tsunami meters, that are tide meters, standard ones, not buoys, but just in the harbors, they had been wiped out in most of the places, except here. You see, these are, the signal is gentler, also if it is 4 meters, okay? But if you give a look here to Kamaishi signal, you see, look at this. it's practically an harmonic signal.
What is the blue?
The blue is modeling. The red is wiped out. But the modeling here, that is Kamaishi, that is here, due to the local bathymetry, look at how beautiful it is, but the period is very long. Look, these are 60 minutes. So it's 30 minutes, 1 hour of a period. Okay, so it's very long. So you see the modeling available in just a few days after, and then you completed this study here. You see now with more measurements. Blue is modeling, red is recorded. And what is important is that tsunami can be considered a very long period. Well, it is a long period signal. Do you remember the source spectrum? I will ask you.
Yes.
Everyone will be asked with source spectrum. Okay? The simple version is like that. Logarithm of amplitude, logarithm of frequency. Okay? And this part here is proportional to M0. Right?
Yes.
And here we have zero frequency. Infinite period. Do we have signals at infinite period? Yes, near field. But where it's not easy, well, we are in Japan, so we have plenty of GPS here. So not on the fault, but on the coast, yes. Near field. 3 modes of the Earth. But if you have also tsunami, because tsunami, they have periods that are very near to zero frequency. Thousands of seconds. If you give a look to, what is it? This one, this is a very long period signal. So actually they are very sensitive to that part of the source spectrum. And the other thing to remember is that so you can use seismic waves, the 3 modes of the Earth, but also tsunamis, to invert and look for the fault. And the inversion of tsunami was giving this, for example. So you have now a direct approach that you can model signals, compare them with measurements, and try to invert for slip on the fault, like the representation theorem. Question: why the pixels of this picture are so large? If you remember the seismic version, in the first that I've been showing to you, what is it? On the first lecture, no, what is it? Of this course, I've been showing to you the inversion for seismic. Oh, by the way, this is one of the pictures that we have been looking a long time ago on the first lecture of the course. Look at the displacement on the fault here. Now you know that's the near field of an extended fault. Look at the patches here. They are large, okay? Why? Because this part, this piece of information is containing long period. It's the near field. If you give a look to, let me show it to you, this one, look at the pixels. Now they are smaller. Why? Because you're modeling higher frequency signals, smaller wavelength. So you got a better vision of that one. What about tsunami? Well, tsunami is giving to you this resolution because their wavelength is large. So you cannot get a better resolution, but it's an important piece of information because it's long period information complementary to the seismic one. So just to say, I hope I do not close the other one. Yeah. Because later, I've been showing to you this. That's the rupture model as inverted by body waves collected around the world, if you remember. That's the rupture, the Tokuoki event that I've been showing to you at the beginning of this course. Now, the rupture, and now you know that is a rupture time. on average it's the length over rupture velocity. That's the distribution of slip on the fault. Here, it's occurring at very high frequencies. Let me show it to you again. Look at the starting of the rupture. This part is the most responsible for tsunami. Because later the rupture was going to the north, and then going back to the south, and what is that? If you remember, the seismic signal was like that. It's very complex. Okay? You have this slide in the first lecture. Okay?
Yes.
Now you know what is PGA, peak ground acceleration. You have also seen the signal in this very hot spot here, Tsukidate event. I've been showing it to you on the last lecture, and now you can see it again and understand it. Okay? So the ground motion is giving to you relatively high frequency information, so tiny details of the rupture. Tsunami is not, is looking at the rupture as a big patch. But it's important because now the source, as felt, as seen by tsunami wave field, is mainly concentrated here. Long period information. So this is the slip on the fault, and this is the seafloor deformation associated to this fault here. Look at the width of these pixels. They are large because tsunami has a large wave. So in the inversion process, you cannot get larger resolution, higher resolution than this. Another animation is showing to us another important characteristic. So this is the animation from the source to the Japanese coast. And if you, let me show it to you again, what is important here to know, what is important here to notice is time. 20 minutes, 45 minutes, it's gone. Okay? And then it's lasting. So please do compare this animation here with the one that we had been looking at the beginning of the course for the ground motion. Now this is ground motion. And if you do remember, this was lasting 6 minutes. And then it's gone. What about the seismic waves after having left Japan? Well, they go abroad. And they create this. Right? And in 90 minutes, they reached the other side of the planet. 90 minutes. Still the tsunami is moving in Japan. Okay? So remember, seismic waves are much faster than tsunami waves. And that's why a tsunami warning system can be designed. So what I'm trying to say to you is that here, look at the time, is 54 minutes, 1 hour. 20 minutes, 1 hour. What's next? Well, the next scale also for tsunami is this one. And I love this part of the animation here. Let's give a look to it. Look at the time here. So let's wait 12 hours, 20 hours. We can sleep. But let's say the day after, the tsunami wave is reaching the American coast. First the north ones, and then the South American coast, let's say after 1 day. Now you could say, what about the amplitude? Oh, that's a good point. Because actually, we have some way here to lose part of the amplitude. Now we know a lot of things. What about an elasticity? Water is very elastic, has a very large Q. So attenuation in the viscous term is not that much. What about losing amplitude here? Well, spreading. Geometrical spreading is taking the leading part in diminishing the amplitude. But not that much. That's why 2 meters here can efficiently propagate around the ocean. Water is very efficient as a propagator. Whales know. They can speak each other in 10,000 kilometers. So actually, also if you have 3D spreading, so amplitude is diminishing, but not that much. That's why tsunami can efficiently propagate there. What about the time? Well, let's use as an average square root of GH. That's why after 24 hours, it's reaching this side of the world. And that's why United States and Japan decided after the 1960 Valdivia earthquake that occurred here to build a tsunami warning system, TWS. Why? Because the Valdivia earthquake, magnitude 9.5, occurred and the day after killed tens of fishermen here in Japan. And they were not knowing what was that. At that time, tsunamis, okay, no one was speaking about tsunami. But in the Pacific Ocean, since the 70s, there is a tsunami warning system. Japanese are cooperating, Australian ones, and of course, the Japanese, and this is the US agency that is called NORF. I don't remember the acronym, but it's an agency, but actually it's the most important scientific center for tsunami forecast, modeling, and hazard assessment. Why modeling? Okay, let's give a look to it again. No, let's. Oh, can I? Come on. Okay. Let's give a look to it. Look at these yellow squares. Those are locations of the first dart buoys, not in front of Japan, we've seen them, but on the other side of a fault, so in open ocean. And look at them. This blue signal here is the recorded one. The red one is the modeled one. You could say, oh, it has been modeled after the event. Yes, but not that after, because actually the trick here is that tsunami simulations have been run and are running also today on a continuous time scale. What they are doing is to build a data set of pre-computed tiny mareograms, if you want, waiting to be summed, representation theorem, to be summed according to the magnitude of an earthquake that they want to model. What I'm trying to say is that in 10 minutes, 20 minutes, they can compute them. So they have a tsunami warning magnitude. Unfortunately, it was 8 point something at that time, and later it was 9, of course. Magnitude 9 occurred here. Okay, let's take all the signals that can be used to model a tsunami source here. Let's put them together. Let's predict. And then they validate. Look at the red with blue. What is important here, that's the first one. You see here? Okay? That's the first, it's this one. Okay? So what they can do in some minutes is to try and to validate. Okay, this is our prediction. What is the most important parameter here? The arrival time of the largest peak. Okay? And it's that one. If the modeling is okay, they issue the other one, and it is this one. Okay? That's arriving. Once they validate, they can give the warning for the other coasts, because now they have, let's say, 10 or 20 hours to issue the warning for evacuation. So one of the messages that I want to give to you is that tsunami modeling is, for example, one important tool. Try to diminish the risk, not killing the hazard because you cannot avoid the hazard, but if you are going to pre-compute and to issue inundation modeling, you can diminish the risk, of course. For example, with an evacuation plan. Of course, you need hours to do that. So it's much more difficult to perform this warning system in smaller basins, like Mediterranean, but smaller, okay? So you have shorter times. But this is a way how to use tsunami modeling, and that's why I was putting here a couple of slides that are sort of a summary, like this. It's not an advertisement, it's just a collection of very simple statements here. Because, for example, with tsunami modeling, you can also try to design what are the better places to, to decide where to put the buoys, dark buoys, okay? That's one issue. So they can drive a monitoring network, for example. The second is to perform, and later to improve, models for forecast and warning. And the last side is to predict. And so we're going now to hazard. That's the final part of the lecture. Now, what about hazard? Since you perform very well in your homework and you have been reading the Netfield 3 pages paper, I'm sure that you did that, right? I'm sure that you didn't do that. But now, what about the hazard for tsunami? Have you been reading PSHA primer?
Yes.
Yes?
Yeah.
Yes, but not
Oh.
complete.
The one on focal mechanisms?
No, just yesterday.
No.
Last.
Okay, the class ones. No, no,
The
I
last.
write down.
You didn't. Okay.
Well, he did.
Okay. Now, what about tsunami hazard? Let's try to imagine what we can do for tsunami hazard. With the knowledge that we have been collecting on Wednesday, we know how seismic hazard is performed. Let's decide the sources. Let's decide sites, for example, a coastline. Maybe we can design occurrence rate, GR low. Maybe what we can do is to study attenuation relationships, or GMPE, ground motion prediction equations. Well, let's call it tsunami motion prediction equations. Can we do that? Yes. And this picture that is coming from Stephen Ward Encyclopedia is giving a very simple, well, you know what? While we have been studying ground motion, we learned that ground motion can be very rich in frequencies. It can have many amplitudes there, so the signal is very complicated. For tsunami, maybe we don't need PGA, the spectral acceleration. What we need is maximum height. That's fine. Can we predict tsunami height? Yes. On a very simple base, with very simple equations, we can draw a map like that. Now, if you give a look to it, it's nothing else. Let's compare it. Let's see if I still have it here. No. Okay. Look. Here we have a parameter, here we have distance, here we have magnitude, right? Good. Here we have a peak tsunami height, magnitude, and distance. These curves are simple, okay? According to the magnitude and to the distance, we can predict them. And you can demonstrate that actually most of the life of a tsunami is like the life of a surface wave. They are cousins of Rayleigh waves. So the decay is going, let's say, as the square root of the distance. That's easy. Then what can we do next? Okay, let's also try to apply a sort of amplification law. You see, this is the ocean depth at the shore, and this is the ocean depth at the source. So what is Stephen Ward is doing here is just to perform this computation. Okay, according to the initial depth and to the depth of the shoreline, these are, for different depths, the amplification factors. And that's the Green's law that I was mentioning before. So now we have magnitudes, we have distance, we have amplification factors, and we can say, okay, what can we do with this? Let's consider all the sources that can contribute at our site with a height larger than a critical one. For example, I'm putting there a tsunami wall of 6 meters. Our critical height is 6 meters, okay? Let's take into consideration all the sources that can contribute with a height that is higher than that. Okay, and this is with this very simple computation. So Stephen Ward is saying, let's take them and let's consider all of them, like in the probabilistic hazard assessment that we discussed 2 days ago. The sum over all the possible events that can contribute. Good. And then you can compute all the ones that are giving a higher height, and then the probability that is not occurring, like what we did yesterday. So you can perform, with very simple basis, a probabilistic tsunami hazard assessment. That's one way. Another way is, okay, we don't care about this. Let's try to be deterministic. So now we have the Japanese coast, we have all the possible sources. Let's compute all the possible inundations that we can get from those sources, and let's take the worst. That's the other approach, right? Good. And this is what the Japanese did. And they were the first in the world to do that. Now, I was collecting these slides from a meeting that occurred on November 2010. So just a few months before the event. And this is nice because the Tsunami Evaluation Subcommittee, that is one of the most advanced in the world, they were making a summary of a tsunami hazard assessment for Japan. They were the first country in the world to perform this, the most advanced. And look, they started a long time ago. And they were so well prepared that after the Sumatra event, 2004, they had been training courses for people around the world, especially in the Indian Ocean, and they were teaching how to deal with that. They visited ICTP, dealing with training course for this. They were great. And what they performed and released is this document that is a sort of a milestone for tsunami hazard assessment. Definitely. Let's give a look to their contribution. They made a point in 2002 and they performed beautiful computations. Look here. This is what I'm doing, for example, with ground motion in my life. Okay? Deal with faults, compute them, and maybe create all the possible envelopes of what can occur. Look, they changed the strike, the dip of the rake of the faults, and they computed the tsunami height. Okay? And for example, for Fukushima Daiichi Station, they perform a specific study because there is an MPP there. Okay, let's be summary of their evaluation procedure. This is November 2010. Okay? The tsunami wall in front of a Tsunami Daiichi MPP is around 5 meters. It's tall, 5 meters. Question, is that tall enough? Salute. Well, it was 6 meters, as far as I remember. Well, they did their computation, and they reached this conclusion here. The maximum water level at the MPP, based on their computations, with this test here, was 4.4 plus an operative meter, 5.7. Conclusion, yes, that's fine. So it's fine. Good. But we were not sure. So we performed, after 2002, probabilistic hazard assessment. Now you know how you can do that. And that's the result. That's called logic tree. Okay, that's the hazard curve. Now you know what is a hazard curve because we have read it yesterday. If you don't believe me, you can give a look here. Rate of exceedance per year of a parameter like PGA. I hope you do remember that PGA is not enough. You need the spectral acceleration in different periods. By the way, that's the rate of exceedance per year. Then you can play the game. Let's take 50 years. Let's take a percentage. That comes later. Okay? Okay. That's the result. Tsunami height, annual probability of exceedance. They took a limit of 400 years. And you get this solution here, 7 meters. So it's fine. Now, question. Was that fine?
That's fine.
No, as you know. Because the tsunami height in Fukushima Daiichi was 12 meters. What was wrong there? Well, oh no, there is an hidden slide somewhere. Was I removing that? No, let me open another one. Because maybe I can add that. I think I updated this one. Excuse me. There is a similar lecture for the broader course. I want to show to you reality. This is a very large file, so it's taking a long time. By the way, so they performed the most advanced. Where is it?
That's a lot of slides.
It's not your course, don't worry. It's another one. But some of the slides are the same. I hope. Where is it? It should be somewhere. But it has to look. Oh, not this one, not this one, this one. Okay. This is another summary, and you see, let's be breakwater. You know, maybe if you had been following the news in those days, that the real damage that occurred at the plant was energy. And energy was gone because Japan actually is divided into, let's say that this is, not sure. Here it is, as far as I remember, 40 Hertz, the power plants, and here it is 50 Hertz. And the earthquake that occurred here was breaking the pipelines. So no more energy. But every MPP has emergency energy systems, like diesel generators, and they had it. But they were here. And water was penetrating there, because the tsunami height was 14 meters. So let me show to you, if I have a picture here. Okay, that's another visual. You see? Prepared 5.7. It's the height that I was showing to you before. That was coming from that slide. Okay? 5.7. Okay. But actually, what occurred was more than 10. So the water was in, and of course, it invaded the building where the diesel generators were. So energy went off. And that was the terrible situation, because the reactor was going down. So no more temperature was increasing, and so the explosion occurred. And if you give a look to these pictures, you see that the water was inundating also beyond the buildings here. And another problem was that, for example, the acceleration of the earthquake, and that's the message also, because we have multi-hazard, the roads were not accessible for the earthquake. So there was a chain of events, of bad luck if you want, but actually, what was wrong in their prediction? What was wrong in... Okay. This is too large, I have to close it. What was wrong here? Bad computations? No, well, you have to know that nowadays the numerical computations are pretty much standard as a code. What was wrong there? Well, what was wrong was this. Okay, this is a map released on January 2008. And it's a beautiful map because it's giving to you, as you can read here, estimated magnitude and long-term possibility within 30 years. You remember 50 years? That's for standard worldwide. For Japanese is 30 years, okay? Good. Let's give a look to them. They're impressive. For example, this is in yellow because they are very scared by an event that could occur there because it's just in front of the Tokyo Bay. And if you look here, magnitude 8 with an 87% of occurrence in the next 30 years. Let's give a look to these ones. Wow, if you want to win money, you can, well, if you don't want, because that's for sure, as you can see here. What about this 90? Oh, and it's 7.5, 71, 76. What about, well, that's low, but this is 20%. Oh, there is also one in front of the Fukushima, 7.4. You see all these tiny pieces had been modeled, as you have seen here. Look, you see? You can define them, in modern words, as scenarios, scenario events. You can perform modeling, you can try to be deterministic, let's take the worst. Or you can be probabilistic, let's take all of them and let's wait for their occurrence, as you have seen. Good. But again, their estimation was 5.7. Someone said that most of the money for this that had been funding this huge amount of studies about tsunami hazard, most of them is coming from NPPs. So actually most of the researchers had been paid by TEPCO, that is one of the corporations driving the NPPs. So they were not that happy that this was not enough. Also because the NPP, Fukushima, was going to be closed the year after the event. So they were, okay, we did our best. Well, maybe the best was to try to understand that what could occur was not this, then this, then this, but all together. Because what occurred on March 11 was not 1, 2, 3, 4 events occurred in 30 years, but just one. With a moment that was larger, because the area was larger. And so magnitude was 9 and not 8. So instead of having 1, 2, 3, 4 events with magnitude 8, we had one with magnitude 9. And the hazard is totally different, because now you can be deterministic, and if you put all of this together, your inundation will be, your tsunami height will be 20 meters, okay? If you want to be probabilistic and you're going to look for more rare events of a magnitude 9, you have to go to lower probabilities here, and you can get 20 meters. So actually what was wrong were not the studies, but the, how to say, definition of the sources. But as I told you, in the past, similar events occurred, and you can see that here. Look at the dots of 1896. In most of the places, they were comparable. So they could have the feeling that a magnitude 9 was possible there, but they did not include it into the computations. You could say it was not in the catalog. So one of the final messages coming from my side is that dealing with hazard, the most important step, and probably the most difficult one, is to assess the sources. in yesterday's talk, Tom Pratt was confessing that in east of US, most of the faults are not very well defined because the occurrence rate is very rare. So, okay, especially for large magnitude events, it's not easy to assess the occurrence of a large magnitude event. Japanese, that is the most advanced country, tried to do that, and actually, let me go back to this. The last map has been published on January 1st, 2011. They just updated these numbers here with some digits, but no one was thinking to consider one event with magnitude 9 instead of 5 with magnitude 8. That's spatial. So you can play deterministic probability, whatever, but the definition of the sources, maybe it's the most important step. So to understand the dynamics of the sources is the most important step. Let me conclude by showing some nice animation that you can find on Stephen Ward's webpage, just to let you to remember that since today, okay, Stephen Ward is a sort of a catastrophic, funny guy that he wants to model also some strange sources, like for example a magnitude 7. Well, from a probabilistic point of view, it has a very low probability to occur, but just in front of New York, of course, it's very provocative, but just to say that in many places, tsunami preparedness is 0. And also to let us to remember that every perturbation of the gravity equilibrium of a fluid can excite a tsunami. That's why he modeled landslides or an asteroid. Of course, it's coming from the top now. Another possible source is a landslide, and this occurred in Alaska. That was very important. It caused a large local tsunami. So landslides can generate huge tsunamis, but usually on a local scale. So they can be 10 meters, but locally. And the final animation is actually from, that's the same, but seen from a different perspective, is a volcanic explosion. And so he modeled what could be occurred in a Santorini island, and the tsunami heights for that one model were tens of meters on some Mediterranean coasts. So please do remember that whatever is changing the equilibrium of a liquid can generate a gravity wave, of course. Throwing stones in a pond or different perturbations. I hope that this link is still active. And also Stephen visited this. Oh, what's happening here? Oh my God.
Forse deve cliccare CTRL. CTRL.
Così?
Dovrebbe funzionare.
I'm back. Sono un po' diversa. Nothing is here? Let's take in the other Stephen Ward. Yes. No question. What is it? Okay. And I think, okay, still you have here the animations. With better resolution. So if you want to look for those animations, still you have the page here. So it's active. What I'm going to do is to add to these slides here also the other ones about the pictures of Fukushima, just to let you to check what occurred in reality. So, okay, my friends, the course is over. You have all the, I hope you have all the PDF. I will update this one on the website. As I told you, during the oral, we will just discuss with logic, not with algebra, the matters that we discussed together. So starting from the, well, introduction was about what we would have been studying, representation theorem, Green's function, far source condition, near source condition, near field condition, far field condition, focal mechanisms, source spectrum, magnitude, different definitions of magnitude, body weight magnitude, surface weight magnitude, Richter's magnitude, moment magnitude, that is the most important one, Q of the Earth, and just a little bit of seismic and tsunami hazard. Okay, that's it. So we are going to meet on 20, right? Have you seen Patrizia today? Wasn't she? No, because she wasn't. Okay, so if not before, let's meet on 20 here around 9:30.
Okay.
Okay?